Yeah, good morning, friends. So, in the previous session, we have had a good revision of all the basic gates. Now, we'll all gates we have seen uh, predominantly these gates, the NOT gate, and OR, NAND, NOR, XOR, and XNOR. So for all of these gates, we have studied what their symbols are. We have studied what their Boolean expressions are, and of course, we have also looked at what each of the gates truth tables are. Okay, so having had this conversation, now we'll go ahead with the actual thing, that is nothing but the implementation of these Boolean gates, or implementation, yes, of these Boolean gates using MOS transistors. Okay, right, so that is the objective of this session. Okay, right, so again we'll start with our very best friend. Okay, that is nothing but the NOT gate or inverter. Okay, see, we have already done the analysis of the inverter, right? Okay, so in particular, the logic style we'll be learning about in this session is called CMOS logic style. Okay, so very important. In CMOS logic style, we'll be using both PMOS transistors and NMOS transistors. Okay, so the general structure of CMOS logic style is something like this. Okay, so this will be VDD. Okay, so near to VDD, okay, we have a network called the pull-up network. Okay, and then we have a connector like this, and then we have one more box over here. Okay, so this is nothing but the pull down network, and this is close to ground. This is nothing but the output. So this is the generic structure of any CMOS circuit. So this is the generic structure of any CMOS circuit. Okay, so let us start with the basic CMOS circuit that we are aware of. We are all very good at the CMOS inverter, isn't it? So how does the CMOS inverter look like? So this is my VDD. Okay, so there are two transistors. Okay, so the first transistor that is nearer to the VDD is nothing but my PMOS transistor. Okay, so I am speaking about this. This is my PMOS transistor, and whereas this is my NMOS transistor. See, if you watch carefully, this CMOS inverter also has the generic circuit structure that we described here. Okay, so there is VDD over here, and VDD is followed by pull-up network. Okay, so this PMOS transistor becomes my pull-up network, and there is a connector, and followed by a pull down network. So in the inverter, my pull down network is nothing but this NMOS transistor. Of course, this is my V in and this is my V out. Okay, so if we dig back to the basics, we know that NMOS transistors, they pass, I think I would have told 10 times in the class by now, they pass a very strong zero, okay, but a weak one. Okay, similarly, what did we conclude about the PMOS transistors? The PMOS transistors conclusion will be exactly complementary to this. Okay, so PMOS transistors, they pass a very strong one but a very weak zero. Okay, so in the generic CMOS structure that we described here, the pull-up network is entirely composed of only the PMOS transistors. Okay, again in the generic structure, the pull-down network is entirely composed of only NMOS. Okay, this should make sense, right? So pulling down means actually taking something down to zero. Okay, and which of the NMOS or PMOS has a strong zero? NMOS here has a strong zero, so that is why only NMOS transistors are used to pull down. Here also pulling up something means making the logic level to VDD, and VDD in digital is nothing but 1. And of course it should make sense if you look at the conclusions that we made here. PMOS passes a very strong one. Of course these two conditions are true when the transistor is on, isn't it? I think we have done so much analysis on transistor, and we are very well aware of the voltage conditions at which the NMOS transistor is on and the PMOS transistor is on. Okay, so these two conditions are true when transistor is on. Okay, now let me start again with the analysis of the inverter, because inverter is central to all digital circuits. So in VLSI, every analysis happens with respect to inverter. So understanding of inverter is very important. Okay, so let us analyze this inverter. Okay, so let me redraw the inverter. So this time around I am not using the arrows on the inverter, but I am using the bubble, okay, in on the transistor, okay, to indicate PMOS. Okay, and I don't use the bubble, and this indicates NMOS. Okay, right, so this is my V out and this is my V in. Now let us go on a case by case basis. Okay, so what happens when V in is equal to 0? Okay, so when V in is equal to 0, what happens to VGS of NMOS? The VGS of NMOS in this case is V in is equal to VG, so VG is equal to 0. Vs is also equal to 0 because source is connected to ground. So VGS is equal to 0. Of course 0 is less than VTH, so the NMOS is actually cut off. Okay, so now what is happening when V is equal to in is equal to 0 for PMOS? So these are the conditions for NMOS. Now what is the PMOS counterpart doing? Okay, when V is equal to 0, what is happening to VGS of PMOS is Vg is equal to 0, Vs is equal to Vdd. So Vgs is equal to minus Vdd, which is of course less than minus Vth. So this transistor is on. Of course, this may be in either linear region or it may be in saturation region. That doesn't matter to us. All that matters is this transistor is switched on, whereas this transistor is cut off. Okay, so what happens in CMOS logic style is when NMOS gets a 0, those transistors are cut off. Okay, similarly, when PMOS transistor gets the input at the gate as 0, they are switched on. Okay, now when Vin is equal to 0, like we discussed previously, so NMOS is cut off and PMOS is on. And when PMOS is on, we have discussed previously here, it passes a strong one. Okay, so one end of PMOS is already VDD, and because this is on, V out will get a strong one. One is nothing but VDD, so V out is equal to VDD. Similarly, we do a similar analysis for V in equal to 1. 1 in the case of digital is nothing but equal to VDD. So when V in is equal to 1 for NMOS, what is happening? VGS is equal to VDD minus 0. This is nothing but VDD. This is of course greater than VTH. So this NMOS is on. Okay. Similarly, what is happening to PMOS? Okay, when Vn is equal to 1, VGS of PMOS, this is VGS of PMOS, this is VGS of NMOS. VG is VDD, and this Vs is also VDD, so this is 0, and this is 0 is greater than minus VTH, and VGS is greater than minus VTH. We all know that the PMOS transistor is cut off. So what happens when V is equal to 1? When V is equal to 1, uh, when V is equal to 1, only NMOS is on, and when NMOS is on, we know that it passes a strong 0, so your output is 0. So let me draw my conclusions here. So when input is 1, when input so when the input is 1, what is happening to NMOS is nothing but it is on. Okay, and when the same input is 1, and the same input is 1, PMOS transistors are in cutoff region. Okay, so this type of understanding will now help us create all other gates that we have learned in the earlier session using our CMOS logic style. Okay, so before going to the gates, so let us analyze this structure. Okay, so let me go to this color. Okay, so I'll take an example. We'll understand construction of different logic gates using CMOS logic style with the help. It is better understood with the help of examples. Okay, so let me take this example. Okay, suppose this is my VDD. Okay, and this is one PMOS. Okay, and this is another PMOS. Okay, so this is my pull-up network. Okay, So in the pull down network, I again have two NMOS transistors that are in series. Okay, so let these two be AB and let these two be AB. Okay, and let this be my V out. So it follows the generic CMOS structure, isn't it? So it has a VDD, okay, and this portion forms the pull-up network, and like we have described earlier, pull-up network consists only of PMOS transistors, and there is a connection, and this is nothing but my, so this is pull-up PUP, this is PDN, my pull-down network, and it completely consists of only NMOS transistors. So whatever structure I have drawn here is nothing but a CMOS gate. But which gate it is? But so that is the big question, isn't it? So what is the gate that this structure is likely to implement? Okay, so let me redraw that gate again. Okay, so let me redraw that gate. Hold on. Okay, so okay, so these are my PMOSs and these are my NMOS. So what gate is this implementing? Okay, what gate is this implementing? Okay, so from the looks it is very clear it is a two input gate. Okay, so the two inputs are nothing but A comma B. Okay, in order to understand which gate it is implementing, if I can come up with the truth table of this particular gate, I can conclude which type of gate this is implementing, because in the previous session we have had a clear review of all the gates and their truth tables. Okay, so right, let us come up with the truth table. So it has two combinations, and two combinations, like I said, will result in, sorry, two inputs will result in four combinations: 0 0 0 1 1 0 and 1 1. So let us calculate this f. So what f is, and depending on f we'll decide what gate this actually is. Okay, right. So in the first case, now a is equal to 0, b is equal to 0. So what was the conclusion that we have previously drawn here? Okay, so when the input is 0, PMOS is on, and similarly when the input is 0, NMOS is cut off. See here, when input is 0, NMOSes are cut off and PMOSes are on. Similarly, when the input is 1, NMOSes are on and PMOSes are off. Okay, now let us come to this first case. Okay, when both inputs are 0, so both these transistors are cut off because these are NMOS, and both these transistors are on. Okay, and these two are in parallel. So what will this output be? So because PMOS transistor passes a strong 1, okay, so this VDD will either pass through this transistor and come as 1 here, or this VDD will pass through this A transistor and can F can become 1. Okay, so this is nothing but 1. Now A is 0, B is 1. So when A is 0, this is cut off. This transistor is cut off. That means there is no path to ground. Okay, right. When A is 0, this transistor is on because it is PMOS. And when B is equal to 1, this transistor is off. Okay, so now in effect, what is the circuit remaining? So this VDD and this transistor is on, and this VDD will pass through this transistor and will appear at F. So this condition also, the output will be 1. Similarly, A is 1, B is 0. So when A is 1, this transistor is on, but B is 0, this transistor is cut off. When this transistor is cut off, there is no direct path from this F to ground. Now let us look at what pull-up network is doing. When A is 1, because this is PMOS, when A is 1, this transistor is cut off. Okay, but B is 0, because B is 0, this transistor is on. Now what is remaining is this VDD will pass through this transistor and appear at this F. Because this is PMOS transistor and it passes a strong 1, F becomes 1. Okay, see now what happens when both are 1 1. Okay, so when it is 1, this is on because this is NMOS. When the B is equal to 1, this is also on because it is NMOS. And when both these are 1, there is a clear path from F to ground. Similarly, what is happening up at the pull-up network? Because A is 1, this is cut off, B is 1, this is also cut off. Okay, so there is no path from F to VDD. Okay, so what will happen now is because this is an NMOS and it is on, it passes a strong 0, and this is also an NMOS, this is also on, it passes strong 0, so the output is nothing but 0. Okay, now if we look at the truth table carefully, we can identify that this truth table is nothing but the truth table of NAND gates. And the expression of NAND gate is A and B whole complement. Okay, right. So I'll draw some very important conclusions here. So you have to listen very carefully. Okay, so you can actually implement any boolean function. You can implement any boolean function using CMOS any boolean function using CMOS logic style. Okay, you have to remember these two very few important techniques. Okay, suppose like you see here, if your boolean expression has an AND operation, okay, here A dot B is happening. If your boolean expression has an AND operation, NMOS will be in series, and similarly PMOS will be in parallel. Okay, so you may write that down. Okay, so so for an AND operation, NMOS transistors, they are always in series, and PMOS transistors will be in parallel. Okay, now we can, because this is complementary MOS, we can always come up and guess the other half. That is, when your boolean expression has an OR, okay, so your NMOS transistors will be in parallel, but PMOS transistors will be in series. Okay, but your output will always be complemented. You see here an AND operation is happening, NMOS is in series and PMOS is in parallel, like we have concluded in the table over here. But the output is complemented, isn't it? There is a whole complement as well. Okay, so in your CMOS logic style, your output is always complemented. Okay, now let us draw the truth table of a NOR gate. Okay, so how will a NOR gate look like? This is the expression of NOR gate, right? Yeah. Now, what is the operation that is happening here? This is nothing but an OR operation. So, in an OR operation, NMOS has to be in parallel and PMOS has to be in series. So let us draw the sorry. So let us draw the NOR gate because it is a OR operation that is happening. Okay, PMOS have to be in series. So your PMOS transistors will be in series over here, and the NMOS transistors will be in parallel. Okay, so this is your pull down network consisting of NMOS transistors. They are in parallel, A and B, and these are your PMOS transistors. Because it is an operation OR operation, they are in series, A and B, and this is where you take the output F. Of course, your outputs are always complementary rather, in your CMOS. Okay, right. Okay, now how do we come up with the circuit for an AND gate? What is the expression? What is the expression for AND gate? The expression for AND gate is nothing but F is equal to A and B. Okay, so how do we draw CMOS logic style for that? Okay, so because this is an AND operation, the PMOS transistors will be in parallel at the same time. Okay, this is VDD. Your NMOS transistors will be in series. Okay, so AB, AB. But like I said, the output of the CMOS, it is always complementary. This is nothing but A dot B under the bar. But what is the expression that we want? We want A dot B. So we know that A dot B bar whole bar is nothing but A dot B, isn't it? So I'll take this A dot B whole bar, I'll put an inverter here. So what do I get? A dot B. Again, what is this inverter made of? This inverter is again a CMOS gate, isn't it? So how does this inverter look like? So this has a VDD, a pull-up network consisting of PMOS transistors, and a pull-down network consisting of NMOS transistors, isn't it? So this is how my inverter looks like again in CMOS. So that finishes my AND gate. Okay, similarly, suppose I want F is equal to A plus B OR gate. I want OR gate again. So this is an OR operation. For OR operation, we know that NMOS are in parallel and PMOS are in series. Okay, so what will this look like? So this is nothing but VDD. So my PMOSs will be in series over here, but what happens to my NMOS? My NMOS transistors are in parallel. Okay, and remember, the CMOS gates always give my output that is complemented. This is A plus B whole bar. But what is the expression that I need from here? I need only A plus B. So what do? I put an inverter over here. I get my required F. Again, what is this inverter? This inverter is also nothing but a CMOS transistor, which again consists of VDD, a PMOS transistor, and an NMOS transistor. Okay, right. So that should give you a fair idea of how to implement any Boolean expression. For that matter, using CMOS logic style. Okay, so let us take another example. So this time let us go with A into B plus C whole complement. Okay, so if you see here, B and C are being ORed. Okay, if it is an OR operation, we know that NMOS will be in parallel, but this B or C is being ANDed with A, and AND operation in NMOS we know is achieved by using series transistors. Okay, so first let me write the pull down network. Okay, so I am drawing the pull down network. Okay, so this is my transistor A. Okay, so this is ANDed with B or C, and in NMOS is nothing but series. So A is in series with B or C, or in NMOS is nothing but parallel. Okay, so this is how it looks like. The pull down network is something like this. Okay, so this forms my B and this forms my C. Okay, now let me come up with the pull up network. In the pull up network, again, so A is being ANDed with B or C here. Again, AND operation in PMOS is nothing but parallel. So here A is in parallel with A is in parallel with B or C. Again, OR operation in PMOS is nothing but series transistor. Okay, so OR operation is nothing but series transistor if it is PMOS. Okay, so this is nothing but B or C. Okay, and this already has a whole complement, so I don't need an inverter over here. I don't need an extra inverter over here because this already has a complement, and from our previous discussion you clearly know that the output of the CMOS gates are complementary by default. Okay, so we'll take one more example so that you become comfortable with converting any given boolean expression to CMOS logic style. Okay, so let us take this example. So let F be equal to AB or C whole complement. Okay, again, so before drawing CMOS, so I'll do the pull down network and pull up network separately. So let me draw the pull down network. Okay, so here A and B are in being ANDed, so in pull down network AND operation corresponds to series transistors. So this is A and this is B. So this AB is ORed with C, and so this is AB. Now it is ORed with C. OR operation in NMOS is nothing but parallel. Okay, so this AB is now parallel with C. Okay, so that finishes my pull down network. Now I have to come up with the pull up network. So this is my VDD. So this is AND operation. AND operation in PMOS transistors is nothing but parallel combination. Okay, AND operation is nothing but parallel combination. So this is two, these two are nothing but A and B. This A and B are now ORed with C. OR operation is nothing but series. So this parallel combination is now in series with this transistor. Okay, and series is nothing but OR operation. Okay, so this finishes my pull up network, and this also has a whole complement, so I don't need to put any inverter here. Already this comes out as an inverted output. Okay, right. Now let us take one more example. I'll give the third example. Let me implement the expression f is equal to a plus b into d plus e. Okay, so this should clear a lot of doubts. This example has a lot of variations. Okay, right. Now let me first come up with the pull down network. Okay, so this is my f. Okay, the pull down network. See, the a is being ORed with b and something else. So if a is being ORed, okay, or in pull down network means the transistor is in parallel. So a is now in parallel with b and d or e. So a is in parallel with b and d or e. Okay, so a is now in parallel with b. Okay, so this should be b. This b is being ANDed with d or e. So AND means series, but it is in series with what? Again an OR. OR means, OR operation means it is again transistors in parallel combination. So this is D and this is E. Okay, so this finishes my pull down network. Similarly, I'll come up with the pull up network. Now I'll draw VDD. Okay, so this A is now being ORed with B and D or E. So OR operation in PMOS transistors is nothing but series. Okay, this is a PMOS transistor. Input is A. So this is in series with what? This is in series with B and D or E. Okay, so this is in series with B that is ANDed with D or E. Okay, so AND operation in PMOS is nothing but parallel. Okay, so this is my B. Okay, so this B is ANDed with D or E. So AND is nothing but parallel in PMOS. So this B is in parallel with D or E, and OR operation in PMOS is nothing but series. So this is B is in parallel with D in series with E. Okay, so in series with okay, so that finishes the pull up. But here, do I have a whole complement over here? I do not have. So what is this implementing? This is nothing but this is implementing F bar, but I want F. So what do I put? I place another CMOS inverter over here. Okay, so that should finish my gate. Okay, so this is finally my F. Okay, so from this session I think you should be able to pick up, or after this session you should be able to draw CMOS logic circuit for any given Boolean expression. If you have any doubts, do write to me on my email or ping me on my Telegram. Thank you.